Homogenization is an industrial process. It is applied to stabilize a liquid emulsion and achieve a more uniform particle size. One of the key functions of milk homogenization is to blend fatty and watery components into a smooth emulsion. Gaulin has been recognized as the pioneer of this process throughout the years. Homogenization primarily reduces fat globules into much smaller fat particles. As a result of homogenization, it also decreases the likelihood of fat globules clumping together. In principle, all homogenized milk is produced through mechanical means, where milk is pushed at high speeds through a narrow opening. The original fat globules are pulled apart by various factors, such as turbulence and cavitation. Homogenization reduces fat globules from approximately 3.5 microns to under 1 micron in size. This also contributes to a total surface area increase of processed fat globules, approximately 4 to 6 times. Milk is homogenized. The physical condition and concentration of fat particles during the homogenization of milk play a significant role in determining the size and distribution of the fat globules that form. Homogenizing cold milk is generally not sufficient to achieve the desired effect. Processing at temperatures below 40 degrees typically results in inadequate dispersion of fat globules. High-fat products are harder to homogenize and tend to cluster more easily than others. Homogenization temperatures typically applied range from 25 to 80 degrees, with homogenization pressures between 100 and 250 bar, depending on the product. Single and double-stage homogenization. Homogenizers may have 1 or 2 series-connected homogenizing valves, which is where the terminology comes from. Single and double-stage homogenization. The two-stage homogenization system is relevant for both single and double-stage processes. The complete homogenization pressure is used throughout the whole homogenization unit. Single-stage homogenization can be used for homogenizing products with a high fat content that require high viscosity. In single-stage homogenization, back pressure is created by the process leading to the homogenizer. In two-stage homogenization, back pressure is generated by the second homogenization vessel. Two-phase homogenization is primarily used to achieve homogenization results where the distribution of fat particles is optimal. Two-phase homogenization allows for the selection of back pressure to ensure maximum homogenization efficiency. Modern homogenizers yield the best results when the ratio of total pressure to intermediate pressure is approximately 2 to 0. The second homogenization vessel also reduces noise and vibrations in the exhaust pipe. Fat globules are disrupted in both homogenization phases. First, to the initial phase. Second, to the next phase. Effect of homogenization. The effect of homogenizing milk has the following advantages. 1. Smaller fat particles mean less cream. Second, a uniform color. Third, a richer flavor. Fourth, improved stability of cultured dairy products. Homogenizing milk also has negative effects. 1. More sensitivity to light. Sunlight and fluorescent lights can change taste. And 2. Homogenized milk is sometimes less suitable for making certain cheeses. The homogenizer. A high-pressure homogenizer is a pump with a homogenization device. A homogenizer is typically needed when high-efficiency homogenization is required. The product comes in with a pump block and is pressurized by a suction pump. The pressure achieved is determined by the back pressure created by the distance between the valve and the seat in the homogenization device. This pressure is always referred to as the homogenization pressure. The actual homogenizer. The plunger pump is driven by a powerful electric motor, using transmissions like belts and pulleys to connect to the crankshaft and drive mechanisms, which converts the motor's rotational motion into the back and forth movement of the plungers. A plunger pump is a type of positive displacement pump, with capacity adjustments possible only through motor speed or pulley size changes. In order to handle higher pressure, smaller diameter pistons are utilized in the installation. The maximum capacity is lowered since each machine size has a limit on crankshaft speed. Larger machines feature longer strokes and possibly more pistons. Often, these pistons are larger in diameter. A high-pressure pump usually contains 3 to 5 plungers that oscillate in cylinders of a high-pressure block. Constructed from very durable materials, the machine features plunger seals. To lubricate the pistons, water is introduced into the area between the seals. A mixture of hot condensate and steam can also be supplied to prevent reinfection when the homogenizer is used in aseptic processes. Plunger pumps create a pulsing flow with fluid acceleration and deceleration, causing pressure fluctuations in the suction line. To avoid cavitation, a pulsation damper is typically placed on the suction line to minimize pulsation effects. Pulsation on the discharge side may lead to vibrations and noise issues. Thus, the exhaust pipe usually has a silencer. Due to its nature as a positive pump, a piston pump cannot function in a series with other positive pumps unless a bypass is implemented. This could cause severe pressure differences and harm to the equipment. If the flow downstream of a high-pressure pump can be stopped, a safety device must be installed that opens before the pipes burst.